So in section P4, we talked about polynomials and we worked with them. We added and subtracted and multiplied them. And now what we wanted to be able to do is we want to be able to factor polynomials. So you may have seen some of this before, but we want to be able to factor because it's an important tool in algebra. Now when we're talking about factoring, factors are things that are multiplied. So it means turning something into multiplication. We're going to be factoring over the set of integers. Now that's important to remember because it could get really complicated if we were trying to factor over fractions or something like that. Okay, so let's go back to what we were doing in the last section. Let's say we had x plus 2 times x plus 1. And these are two binomials that are being multiplied, right? So we have two factors, x plus 2 and x plus 1. We can multiply it out. That's what we worked on. So let's say we FOIL it. X squared plus 1x, you don't need the 1, plus 2x plus 2. So that would be the FOI in FOIL. And then we would combine like terms, and we would get this. Okay, so now we have a trinomial. It's in standard form, and we have three terms that are being added together. What we're trying to do in factoring is go from this stage, we want to go back up to the multiplication stage. So it's like unfoiling, like we want to just run it backwards. Now there's different types of factoring, some strategies, and we're going to give you those in this section. Now, let's say you have something. Let's say you have x squared plus 7. There's no way to turn that into multiplication over the set of integers. And when that happens, we say it's prime. Sometimes they'll say not factorable. So if you can't factor it, it's said to be prime. Okay? All right. When we talk about factoring completely, we're talking about breaking it down as much as possible. Think about back when you learned about just numbers and factoring and the factor trees. Let's say you had 12 and you said, oh, 12 is 2 times 6, right? But if you were doing what we call a prime factorization, you'd have to break the 6 down, right? 2 times 3. So when we're factoring with polynomials, if we can break it down more into other factors, then we have to do that. Okay, so one of our strategies, the first one we do, is called the greatest common factor. And so what we're looking for, if we have something like 12x cubed plus 8x plus, think of a good number here. Let's try to think of a good one. 24. Say you had that. Well, if you're looking for the greatest common factor, you're looking for something that you could take out of all three of them. Okay? So it's like you're undistributing. Undistributing. In this case, they don't all have an x, so I can't factor out an x. But if I look at the numbers 12, 8, and 24, all of those are divisible by 4. So that's what I would factor out, a 4. And then what you're doing is you're dividing each one of those by 4. So you'd have 3x cubed here plus 2x plus 6. And you'd be done. Okay? You can always check it by multiplying it out. So you can check your factoring by multiplying. So on tests for factoring, I always tell students you should get them all right because you can always check them. It doesn't happen that way, but you know, in theory, you can always check it by multiplying. All right, so here's our answer. That's factored. And it is factored completely. Okay, to check it, I would have to multiply, and in this case, that's a distributing thing. So I'd go 4 times 3x cubed, which is 12x cubed. I'd go 4 times 2x, which would be 8x. And I'd go 4 times 6, which is 24. That should be the original polynomial. If it's not, then I've made a mistake somewhere. Now, on that problem, I'm kind of out of room, but let's say you looked at the original polynomial. I'll go down here where we have it. And you said, oh, they all have a 2. And you would do this type of thing. Well, if you multiply it out, you're right. 2 times 6 is 12. 2 times 4 is 8. 2 times 24 is 12. I'm sorry, 2 times 12 is 24. And that works. The problem is this is not factored completely. Not factored completely. Because you could take out a 4. Now, if you did something like that and you looked at what you had left, you would see, oh, I can still take out a 2. So then you could take out that 2, and then you'd have 2 times 2, which would be 4. And then this would be the 3x cubed plus 2x plus 6. So you can still fix it, but it's better if you can get the greatest common factor first. And in this case, that example, the greatest common factor was 4. Okay, so now we want to practice doing the greatest common factor. So I'm going to look at these two terms right here, and I'm thinking, what's something that both of them could be divided by? Like, what's the biggest thing? So think about that for a minute. Okay, hopefully you said 9, because 9 will go into 18, and 9 will go into 27. And then look at the x's. You have x cubed here and x squared here, so you can take out x squared. So if they all have the variable, it goes by the lowest exponent on the variable. That's how many you can take out. So they all have x squared at least. Okay, now if it helps, you can just write your common factor. That's the greatest common factor is 9x squared this time. And then you're going to divide them both by that. So, you know, you can go 9 goes into 18 2 times, x squared goes into x cubed x times, or you could use your exponent rules, or you could have just seen, oh, I usually think like, what times 9 would be 18, and what times x squared would get me x cubed. That's kind of how I think of it. Okay, and then the other one's going to be 3, just a plain 3. All the x's came out because it had x squared, and those came out. Now, we can check this. This is our answer. It's multiplication because you've got 9 times x squared times 2x plus 3. So it's factored. And then I can check it by multiplying with the distributing. 9 times 2 is 18. And I get x cubed because you got x squared and then another x. And then multiply here. You have 27x squared. So, yep, it checks. All right. Now, this next one's very visual. So, you're looking at B here, and you've got x squared, x plus 3, plus 5 times x plus 3. So remember, factoring, we're trying to get it in terms of multiplication. So you might be saying, well, it is multiplication, right? X squared times x plus 3, right? But if you look at the whole thing, what's the overall operation? It's right here. It's addition. It is not multiplication right now. You have stuff plus stuff. I know that's not very mathematical, but that's what you've got here. So it's not multiplication. We don't want stuff plus stuff. In the end, we want stuff times stuff. Okay, so let me rewrite it so you can see it, because I've written all over it. So how can I make this stuff times stuff? Is there something that they both have, a factor they both have? Well, the answer is yes. They both have x plus 3. This is a binomial that they both have. So what I'm going to do is I'm going to take that factor out of both of them. I'm dividing them both by x plus 3. So what's the GCF? X plus 3. Now, it doesn't matter if you put the GCF in the front or the back. I'm going to put it in the back, so I'm going to have x plus 3. But if you like it in the front, that's fine. I usually put it in the front, but I'm trying to get better about putting it in the back. Now, what do you have left? Well, those cancel, so you'd have x squared, and those cancel, plus 5. And that's the answer. Because now you have stuff times stuff. Now, you might be thinking, well, how do you check that? Yeah, that's a little tricky. So you're taking this and you're distributing it there. So x squared times x plus 3. And then you're taking this whole binomial times the 5. So it's plus 5 times x plus 3. And that's what the original was. Now you could have a question like, why didn't we distribute here? I don't know. They didn't start us out that way. We just went to the original problem. Okay, but we'll see more of this and we'll work on it. It might be a little confusing now, but we'll keep working on them.